All right, welcome to The Explainer. Today we are talking about something huge. We're talking about the invisible glue that holds, well, everything together.
Have you ever really thought about it? What's stopping an astronaut from just floating away into the blackness of space? Or for that matter, what's keeping your feet on the ground right this second? It's all the same thing, a single, invisible force.
And that force, of course, is gravity. So today, we're going to decode its secrets, starting with the OG, the guy who wrote the rulebook, Sir Isaac Newton. Okay, so where do we even begin with something so massive? Well, we start with a formula, the master equation that kind of describes it all. Now, I know, equations can look a little intimidating, but trust me, this one is beautiful. It tells a really simple but incredibly powerful story about the pull between any two things in the entire universe.
First up, we've got F. That's just the gravitational force. It's the pull, the mutual attraction between two objects. You can think of it as the answer we're trying to figure out. Then you have M1 and M2. That's just the mass of our two objects. And this part is super intuitive, right? The more stuff something is made of, the more mass it has, the stronger its gravitational pull is going to be.
And then there's R. That's the distance between the centers of the two objects. Now, this is a really important part. See how it's squared in the equation? That means gravity gets weaker fast as things move apart. Like, if you double the distance, the force isn't cut in half, it drops to just 1/4 of what it was. It's a huge deal.
And finally, the secret sauce, G. This is the universal gravitational constant. Think of it like a volume knob for the entire universe, one that's permanently set to a specific number. It's the magic number that scales the whole thing and makes it all work.
So, just how big is this G? Well, it's actually incredibly tiny. We're talking a decimal point followed by 10 zeros before you even get to a number. And this is the key. This is why gravity, even though it can hold entire galaxies together, is actually the weakest of all the fundamental forces in nature. It's just not that strong on a small scale.
All right, enough with the letters and symbols. Let's make this real. Let's see how this whole equation plays out on a scale we can actually understand by plugging in some numbers. So for our first example, let's take a regular 10-kilogram bowling ball. That's about 22 pounds, and calculate the gravitational force between it and, well, the entire planet Earth. And you can see here, Earth's mass is just mind-bogglingly huge.
Okay, so you plug all that into the formula, you crunch the numbers, and what does you get? About 98 newtons. Now that's a force you can definitely feel. It's basically the feeling of holding that bowling ball in your hand. We have a much simpler word for it, though. We just call it the ball's weight.
Okay, so that's the Earth. What about something smaller? Let's calculate the force between two regular people standing pretty close to each other. They both have mass, right? So according to the formula, there has to be a gravitational pull. The question is, how much?
And the answer is practically nothing. We're talking less than a millionth of a newton. It is an astonishingly small number. Remember that super tiny G constant we talked about? Well, this is where it really shows up. The force is so weak, so minuscule, that you'd never, ever feel it. And that's why, you don't get sucked towards the person sitting next to you on the subway.
And putting these two side by side really just drives the point home, doesn't it? Gravity is this epic, universe-shaping force, for sure. But for you to actually feel it in your day-to-day life, you need at least one of the objects to have a truly planetary-sized mass. And check this out. This is where it gets really cool. If you take this law and you put it next to Newton's other super famous equation, F equals ma, you can actually mash them together. And when you do, you can figure out this little g, the acceleration due to gravity. What this means is we now have a universal recipe to figure out how fast stuff falls on any planet in the universe, as long as we know its mass and its size. Pretty amazing.
Okay, so this all leads to a really fascinating and honestly a pretty misunderstood idea, the totally counterintuitive physics of what it means to be in orbit. So think about it. If you're swinging something around on a string, what keeps it from just flying away? It's the string pulling it inward, right? That inward pull is called centripetal force. Well, for a satellite, or even for the moon orbiting the Earth, there's no string. That inward pull is provided by one thing and one thing only, gravity.
Right, so that constant inward pull is just Earth's gravity. And this is the mind-bending part. Astronauts and satellites aren't actually weightless, not at all. They are in a constant state of freefall. They're just moving sideways so incredibly fast that every time they fall down a little, the Earth's surface curves away from them by the exact same amount. They're literally falling around the planet. That is what orbit is. Okay, so now we have this amazing, universal law. It works for apples falling from a tree, and it works for satellites whipping around the planet. So armed with this knowledge, let's zoom way out and do something that sounds impossible.
Believe it or not, we can actually weigh the sun, and we only need two pieces of information to do it. First, we need to know how far away we are from it, that's our orbital radius, r, and second, we need to know how long it takes us to go around it one time, that's our orbital period, t. So if we take those two numbers, which we know pretty precisely, and we plug them into a slightly rearranged version of Newton's law, we can solve for the mass of the thing in the middle, the sun. We can literally put our own star on a cosmic scale right from our desks here on Earth.
And there's the answer. That is a truly staggering number. We're talking about a 2 followed by 30 zeros. Just let that sink in for a second. We figured out the mass of our star with incredible accuracy, and we never had to leave our own little planet to do it. And that just goes to show you the power of a single universal rule. It connects everything, from a simple bowling ball on Earth all the way to the fiery heart of our solar system. It really makes you wonder, doesn't it? If one elegant formula can weigh a star, what other incredible cosmic secrets are just sitting out there, waiting for us to find them?